Hi, my name is Isaac Trader, and I'm going to present the solution that I found for the analysis problem 1B for ME4511 Engineering Analysis. The problem description deals with a three-bladed helicopter rotor that has been disengaged from the motor while spinning at an initial speed of 60 RPM, which is shown here by the omega term. This is a figure showing the approximate side or shape of the rotor system, which is going to have blades that are 5 meters in length by 0.2 meters in width. The mass of the blades is going to be 50 kilograms. The mass of the shaft, as you can see here, is 100 kilograms. And because the motor has been disengaged from the rotor, there's not going to be any driving force behind the blade or behind the rotor, so the motion will be slowing down, which the drag force acting, which is shown here by the forces drawn, is going to be slowing the rotor down, as I said before. The coefficient of drag for the drag force is going to be 0.2. The radius of gyration for the shaft in the middle of the rotor is 0.2 meters. The assumptions we're making here is that there's no pressure drag because the cross-sectional or the frontal area of the blades is so small that it's essentially negligible, and because and to simplify things even further, we're also going to assume that the rotation on the bearings of the rotor is going to be frictionless. In order to calculate the overall motion of the rotor, we're going to sum the moments times the mass moment of inertia times alpha. And the mass moment of inertia, as you can see up here, is calculated for the blade using the mass of the blade times the length squared plus the width squared divided by 12. And because that equation only gives you the mass moment of inertia through a center point in the rectangular geometry, we're using the parallel axis theorem, which will essentially move the center of the center of motion to the center of the geometry of the rotor. So we're going to do that, we're going to take the mass of the blade times the distance that we're moving it squared and add that to the mass moment of inertia for the rectangle. Then also to calculate the mass moment of inertia of the shaft in the center of the rotor, we're going to use the radius of gyration, which is 0.2 meters squared times the mass of the shaft. Then to calculate the moment acting on the rotor, we're going to use an equation which is the moment is equal to the radius or the moment arm times the force of the drag. And then because we're calculating the moment across the entire span of the blade, we're going to have to integrate it. And to do so, we're going to take our force of the drag equation, which we have here is 1/2 rho times the coefficient of the drag times area times omega squared times r squared, and the rho being the density of the air. And when we take our derivative of the force of the drag to put it in the terms where we can integrate across the entire blade for the moment arm or the moment acting, where we will end up with this equation and then plug it in, multiply in our radius here to here, so we have an r squared times omega squared, and when we integrate we get 2/3 rho c sub d r to the 4th times the width times omega squared, which with omega being the rotational velocity. Then in order to develop the differential equation that governs this motion, we will be replacing the beginning term of the force equation as we will be multiplying by 3 for each blade, so there's 3 blades, we multiply by 3, which cancels the 3 off, and then we're taking the entire rest of the drag force term without the omega squared and putting it into a constant beta because it's not going to change. and then we are solving the differential equation to, when we solve the differential equation, we end up with, or separate the differential equation, we get 1 over beta times the quantity t plus c, and then we solve for arbitrary constant c, and we get 1 over 60 beta. The final equation to relate the time that we developed, the time that was included by taking the differential equation, we get that the rotational speed is a function 60 over 60 beta times the time plus 1. And when we plug that equation into MATLAB, we get a figure that looks similar to this, where it starts at 60 RPMs and it's approaching 0, and it has a kind of a exponential sort of shape to the figure here. And then to validate what I found, which I started with just kind of a expected result of what I thought we should see, and I found that I assumed that we were going to be starting at 60 RPMs as we were given. That was the initial condition. So we're starting at 60 RPMs, and then we're tailing off to 0, which is what I expected. And I expected the shape of the graph to look somewhat like this, simply because the force of the drag is more intense at the beginning. We are going to be we're going to have a steeper slope at the beginning, slowing down, and then we're eventually going to kind of level off close to 0. But because we're assuming there's no friction and the force of drag is velocity dependent, it's never actually going to reach 0 the way the math is set up currently. The second consideration I took in validating was that the design intent of why they would want it to spin for this long. And my design intent, I did some research online and found an article detailing autorotation, which is a phenomena that is created created when the motor of the helicopter, if something were to happen while in flight, if the motor was to shut down, to keep it from stalling the blades, they would disengage the motor from the rotor, and it would continue to spin due to the large mass moment of inertia that it possesses. And in that case, that would give the pilots an opportunity to hopefully land safely before they would have to deal with any sort of crash. Now, because it drops off so quickly here, because 60 RPMs is not typically what a helicopter would operate at, so it's more in the neighborhood of like 300 RPM. And so given that, you can assume that they would probably have approximately 2 to 3 minutes at least to land it, based on the general shape of the graph, if you were to extrapolate that out to the 300 RPM starting velocity. Now, the third validation method that I used, I compared my ease, or I plugged the same equations into ease that I did in the MATLAB, and I took and found the same graph over the same amount of time, and as you can see, the graphs are very similar. Therefore, we can assume that it was plotted correctly. Then my third method of validation, I took and entered my force drag equation into MATLAB and did an integration, and using the integration function, I came up with a similar equation at the end. The alternative method that I used to calculate or do my final validation, I used the conservation of energy, which is the derivative of the energy with respect to time, and so as energy changes over time. Because there's no heat transfer and there's no gain or loss of mass, we are neglecting those terms from that equation, so the only thing we have is the negative of power. So we set up our kinetic energy equation, which is going to be the 1/2 the mass moment of inertia times the rotational velocity squared, and it's going to be equal to -3 for 3 blades times the moment created by the drag times the rotational velocity. And when we develop out or carry that equation out, and we end up developing the exact same differential equation that we started with in the first place. Any questions?